Hello and welcome to the Span Tree Protocol video tutorial. I've made this video as a part of my internet working class project, and I'll be covering the basics of Span Tree Protocol, its terminologies, its operations, while I'll also be doing a few simulations in Cisco Packet Tracer and running a few commands on Cisco switches. So this will help us get to learn a few commands and also see how STP resolves itself in practical networks, how we can see how packets traverse across the network through these simulations. So let's quickly I'll be moving between the PowerPoint slides and the Cisco Packet Tracer software in between the presentations whenever I come up with simulations. So let's go into the presentation now. Okay, the Span Tree Protocol, or in short STP, is standardized as the IEEE 802.1d. It's an IEEE standard. Let's see what our agenda for today's presentation is. We'll primarily be focusing on why and when we need a loop avoidance protocol. And then we'll see what problems does STP solve and how does STP solve these problems. Then we'll go into the terminology and operation of STP. And finally we'll conclude with limitations and conclusion. So let's see why we need a protocol in place. It's always better we understand or analyze why a protocol came into existence in the first place. So we all know that the internet is a web of various interconnected network elements, right? So it's basically a mesh topology out there where we have redundant links connected between nodes. Because we always prefer redundancies. This is because we have two paths that offer protection. We always need a backup path in case our main path goes down. So this is why redundancy is always preferred in networks. You see, you take any network, they always choose to have linked and device level protections. But unfortunately, redundancy comes at a cost, and that's called as switching and bridging loops. We'll see what a switching and bridging loop is next, and we'll see how dangerous they can actually be. As you can see here, I've got a very simple network of two switches which are connected back to back, and they have a redundant link configured as well. I've got a client connected to one of the switches and a server to the other. Here the okay, let's assume that the switch has not yet learned any MAC addresses. It has just been installed and it hasn't learned any MAC addresses. It's fresh. And let's also assume that the PC is just booted up. So what happens when a PC boots up? Usually a PC sends out an ARP request, right? We know what an ARP message is. So the ARP message is basically a broadcast message, which I've indicated with this green arrow mark here. So let's imagine this to be our ARP message. So what happens when an ARP message, the broadcast message, reaches the first switch? How does the switch handle broadcast messages? Well, the switch actually forwards broadcast messages out onto all its interfaces except the one it received from. So this is how a bridge is going to act on broadcast frames. So this broadcast frames which the bridge received on interface 1 is going to be sent out on all its other interfaces. So as you can see, I've indicated with two more packets. I've just differentiated them in color because we'll be seeing what our second problem is, and that's why I've differentiated them in color. But basically they are duplicate packets. They are the same packet actually. So this is giving rise to our first problem of packet duplication. A switch copies the same packet onto all its interfaces, thereby creating duplicate copies of the same packet, which are actually unnecessary. Now let's see what happens when the ARP message reaches the second switch. So as you can see here, the second switch also handles broadcast messages in the same way as the first switch did. It forwards it to all other interfaces except the one it received from. So the second switch is forwarding one copy of the packet to the server where it was originally intended to go, but it's also forwarding another copy of the packet back into the network. So you can see this green curved line, right? So this indicates that the ARP broadcast is coming back into the network. So because of the loop, this green frame is reaching back to the switch 1. So this is giving rise to a second problem, which we call it as broadcast storms and flooding, because the same thing also happens to the red packet. The red packet comes to second switch. The second switch broadcasts the red packet out onto all the interfaces, so a duplicate copy goes towards the server, whereas another copy comes back into the network again. So originally we had one packet coming into the network, which is now got duplicated, multiplied twice, and these two packets have now started looping around in the network. So imagine if multiple packets were to be sent from the client to the switch, all these packets would have got duplicated and they would have started flooding the network, so giving rise to what we know as broadcast storms and flooding. This is a very major problem created by loops. Now let's see what a third problem is. What happens to the ARP message when it comes back to the switch 1? Originally, switch had learned the MAC address of client A through interface 1, because client was connected to the switch through interface 1. So it had accordingly updated its MAC table also, saying that okay, I can reach this particular MAC address on interface 1. But because of the loop, switch is receiving the same packet which has the MAC address of the client through different interfaces as well. He received the green packet through interface 3, and he received the red packet which is same as the green packet containing the same MAC address of the client through interface 2 as well. So at different points in time, he is receiving the same source MAC ID on different interfaces. So he is constantly updating his MAC table entries, leading to a third problem, which we call it as MAC table instability, or we can also call it as MAC table convergence. So these are the three main issues created by loops in networks. But these issues also give rise to secondary issues like traffic congestion and increased CPU utilizations, eventually leading to traffic loss. So congestion is primarily because broadcast storms are eating up or choking up your bandwidth and leading to congestion, and MAC table instability and constant packet processing. The switch is constantly processing huge number of packets and updating its MAC table every now and then. This gives rise to increased CPU utilizations on the switch. So eventually it's going to have a lot of bad effects on the network, on the processing capability of the switches, eventually leading to traffic loss. So this is how dangerous loops can be. We can actually see this with a small simulation in Cisco Packet Tracer. But the important thing to note here is that by default the switches here come with STP enabled, so you initially have to disable STP on them if you have to carry out this simulation. So I'll just show you how you can disable STP on these switches. First we would go into the switch and then the spanning tree. You first like to go into the configure terminal, yeah, and then we would go into the spanning tree, or here we can type the command no followed by spanning tree space VLAN followed by VLAN number 1. So by running this command you can disable STP on the switch. So when you run the same command on the second switch as well, both these switches are now STP disabled. So you can then create how many of redundant links you want and just check what happens because of a loopy network. So as I've already done all that, let's first enable the interfaces on the client side, before which I would have to start my autoplay capture. And as you can see here, I've filtered out only ARP because we don't want to get confused with any other packet. So I've filtered only for ARP here, and let me turn on auto capture. Now I'll enable both the interfaces on the client such that they start forwarding their ARP packets, and as you can see, the green packet is nothing but the ARP broadcast. Let's start autoplay. So the PCs have forwarded the ARP messages out onto the switches, as you can see here, and the switches are now forwarding those packets to the PCs. But you can see multiple packets getting created now. As you can see, there are three packets that are getting created. This is because we have a loop and the switches is forwarding packets out onto all its interfaces, and the process never seems to stop. As you can see, ideally if you had created the same setup with just a single link, the process should have stopped by now. But as you can see, the process is going on and on. It never seems to stop. So this simulation helps you understand the effect of loops. It's creating a flooding now. It's creating broadcast storms in the network, which we were discussing previously in the slides. So let me stop the simulation now. I'll also be showing you how MAC table instability is caused. So we can see the MAC address of this PC first. So as you can see, MAC address of the PC is 60. Okay. Now let's go into the MAC table of the switch by typing the command show MAC address table. Now, yeah, here you can see that the MAC address of the PC should have ideally be learned on interface 1 of the switch, because interface 1 is what it's connected to. But you can see here in the MAC address table that it's learning the MAC address of PC0 on interface 4. This is because of the loop packet which received the switch, which came back to the switch through interface 4. You can verify the same thing on the other switch as well. So let's check the MAC address of the PC first, which says 30. Now let's check the MAC table of the switch. Show MAC address table. Yeah, there you go. It's being learned on interface 4 again, but ideally it should have been learned on interface 1 here as well. So this is our MAC table instability problem that we were discussing. So I hope the simulation has helped you understand what sort of problems loops can cause, and with respect to broadcast storms, flooding, packet duplications, and it never seems to stop. It continuously keeps rotating in the network. This is because it's important to know that there is no concept of TTL. There's no concept of time to live decrementing in L2 networks. So as TTL is not decremented, these packets seem to forever keep looping in the network. Now let's go back to our slides. And yeah, now how does STP resolve these loops? Loops are resolved by STP by primarily forming a structure that is known as a tree. So what's a tree? A tree is something very analogous to what we see in nature. It's very similar to what we see in nature. Like, it's got a root, and then it's got branches and leaves. So the whole structure seems to branch out from the root such that there's no loop in between. Similarly, STP also generates a tree structure out of a closed or a mesh topology such that all links seem to diverge from the root. So it basically converts a closed structure into an open structure such that you don't have any loops in your network. So STP does this by calculating something known as the minimum spanning tree. It runs an algorithm to check the least cost path, and it calculates a minimum spanning tree such that it eliminates all redundant paths to a particular destination, thereby forming a tree structure. But STP also does another thing. It provides redundancy in case of link failures. This is a very important feature of STP. Not only does it break loops, it also provides redundancy by enabling an alternate link if your main path goes down. So this is a good feature of STP, or else it would have probably never have been used if this feature wouldn't have been there in STP.